All right, everybody. Welcome to day 40. Just before I started class today, I thought I'd reach out to our correspondent over on the internet, and she just has some important information to give us here this morning. So,
Hi guys, it's Allie here today with your makeup call. Once again, just remember to click subscribe on that little button down below to be able to watch all my fun videos. Thanks guys, I really appreciate it. So today we're going to start off by doing a really pretty, just classic red lip. It's one of those elegant, sophisticated looks every girl should know how to do. It's just something fun you can do when you're going to go out on a night to town, kind of a classy, mature look if you're going for. Just a few helpful hints before we start off is once you're doing your makeup and your foundation and your eyeshadows and all of that, just make sure not to do too bright of a blush or too deep of a bronzer or too crazy of eyeshadow colors, because then you're going to look like a clown. It's going to be too much. I mean, your lips are going to pop enough that that should be the basis color of your face. Make sure you can do a heavy eyeliner if you want, or even a lighter one. Stick with some natural and neutral colors. As you guys can see here, I did some browns and some just natural, so like hint of black, just to get a little bit color there, but not too much. All right, let's get started on the red lip. A lot of girls like to start with the lip liner, but I like to start off just with doing my lipstick. I'm using my mom's Bobbi Brown. It's the red number 10. There you go. It's a really pretty color. She just got it brand new, so shh, don't let her know we're using it. So let's just start. You want to start by filling in that little top part. It looks like a heart on your lip. Just kind of get it in there. Fill it in a few different times just to kind of get a real deep color. And then kind of go in here at the bottom.
oh my God, Allie, are you okay? Gosh, I was learning so much, but then an earthquake struck the San Andreas Fault. So today,
Hi guys.
before we get started, sorry, Allie, I'm cutting you off. Before we start on earthquakes and shaking, just some logistics. Okay, so this Sunday, there is only a couple of things due. Just the two short lecture quizzes from today and Wednesday. There'll be no lecture quiz on Friday. There is no lab assignment. You're done with those. And there's no reading quiz. We're done with that too. Okay? So, you have a final exam, and that is on Thursday, May 7th. It's going to be a 2-hour exam that you'll take on Blackboard. If you have a conflict on May 7th, if you, unfortunately have like 3 exams scheduled on the same day, contact me, and then we can figure out like if you could take it on Friday the 8th. I remember doing that in college and having multiple exams on the same day, and it really sucks. So I'm happy to just like change the due date for people if they need it, but I would prefer if everyone could try to take it on the 7th, okay? So this will be an open book, open note exam, but unlike the second midterm, I'm only going to give you one attempt. First midterm was kind of like a 100-mile-an-hour fastball. Second midterm was kind of like playing t-ball. I want to maybe make it like, I don't know, corporate softball level of an exam this time, okay? So like a little bit more challenging than the second midterm, okay? So I'll have a similar question format as previous exams, and it will be cumulative, but most of the material, 2/3, 67%, will be on material presented starting day 28 through 42. So that's includes weathering and sediments up to the rest of the semester. So through earthquakes, basically. And then a third of the material will be drawn from the previous portions of the class, okay? On Friday, I will just do a review session, like a recorded lecture of topics to review. You can always send me messages on Teams or email. If you have specific questions and want to chat, I'm happy to do that. I think I've been pretty good about responding on Teams to questions as fast as I can. So, and then I guess during the exam week, we can think about like times of when I'll be available for review times. I'm supposed to attend a digital conference next week, and so I don't have total availability, but I will have almost as much time as necessary. Okay, so let's just start with reviewing what actually is happening during an earthquake is the release of different seismic waves of energy, right? And we can classify them into two broad categories, body waves and surface waves. And our body waves are those which are released during the earthquake and travel through the interior of the earth. We have primary waves, and they are compressional, meaning it's like force push, right? And they travel the fastest, and they don't cause damage. Secondary waves are slower than primary waves, and they have a sinuous pattern to them. And because of that sinuosity, there is a shearing stress that they create, and so they are more damaging. The other type of seismic waves that we can have are surface waves, right? And these are slower than the body waves, and they only travel through the crust. And they are typically what causes most of the damage during an earthquake because there is lateral and vertical motion in shallow areas, right? So we have Rayleigh waves, which are the vertical surface waves, and then the Love waves, which are the horizontal. Okay. All right. So we have all these different waves, but how do we actually, take shaking on the ground and then convert it into something that we can scientifically understand? So the way that we measure earthquakes is with devices called seismometers. Okay, so a seismometer measures the three directions of ground movement in the X direction, the Y direction, and the Z direction. So the X direction would be east to west, Y direction is north to south, and Z is vertical, right? We live in a three-dimensional world. Okay, the way that a seismometer is designed is that you have some frame, right, that's bolted into the ground. And on that frame, there's a scroll with some graph paper, and it is fixed, right? So the frame of this device is fixed in place. There is a spring-loaded weight with a pen attached to it, or a pendulum with a pen attached to it that is able to move freely with motion. Okay, so the frame of the seismometer stays fixed in space, but the pendulum or the spring-loaded pen can move freely when there is shaking. Okay, on the seismometer there is a scroll of paper which is constantly spinning, and because it is spinning, we know the time that is passing. We monitor any vibrations and changes through time. So we can monitor what types of seismic waves are arriving and the direction that they are occurring. Okay. So I show this GIF of Randy, the geologist from South Park, and there's a problem with his seismometer, right? Because he doesn't have the three directions, and that pen is not able to move freely during shaking. It would only be monitoring, whatever is going on in the XY direction. Anyway. So on a seismometer, you record seismograms, right? So like these are the actual graphs that are plotted during an earthquake, okay? So on a seismogram, the x-axis is the time that is elapsing, right? Because that scroll is constantly spinning and the pen is recording what's going on. And then the amplitude is the y-axis, and that records how much shaking has occurred in that direction. Okay. There are a couple of important things to note here is that there's a characteristic pattern to seismograms during earthquakes. Because primary waves travel the fastest, they arrive first, right? So on this seismogram, the first agitation we receive is the primary wave. Then there is a span of time until we receive the secondary wave. The amplitude of the secondary wave is greater than the primary wave because it is a shearing force as opposed to a compressive force, right? Because if you go like you push someone, right, you are only feeling the direction coming directly at you. But if you have a shearing force, it's going back and forth, and it is going to record a larger amplitude swing. After the secondary wave arrives, then the surface waves arrive. Okay? The important things to remember here, and for the next couple of slides, is that we want to pay attention to the delta t, meaning the difference in time between the arrival of the S waves and the arrival of the P wave, and then the amplitude, okay? So, of course, this is just a one-dimensional seismogram, but of course we are measuring seismograms in 3 directions, right? So this is what a seismogram looks like from a single station where you have the X, Y, and Z directions recorded. Right? So we see the same arrival time of P waves in each component direction, right? And we also see the same arrival time of the S wave, but the shape of this graph looks different in these directions based on what type of shaking is occurring and the direction it's occurring, right? So the X direction are east-west and the Y direction north-south. These look like they have similar amplitude, right? But there's a different pattern to them. Versus the vertical Z-axis, right? There is less magnitude or less of an amplitude of shaking in that direction. So this is getting to a part of earthquake science which is beyond what we necessarily need to know, but you can mathematically figure out what type of earthquake is occurring based on these different shaking motions in the X, Y, and Z direction. Okay. So now I'll show a good video that explains. Oh man, love when that happens. All right, we'll just do this. Okay, so now there's a good video here that I'll show.
Exaggerated look at how a house would be affected by each direction of motion.
All right, sorry.
Earthquakes produce different types of seismic waves that can be identified on seismograms. But did you know that each seismograph station produces 3 different seismograms for each earthquake? Why is that? Doesn't one tell you how big the earthquake was? Earth's movement is 3-dimensional, and one component only reflects one direction of movement. If a station had only one component, you would only know about movement in one direction. Different instruments on the seismograph measure 3 types of motion: up-down or vertical motion, north-south motion, and east-west motion. Let's take a close-up, exaggerated look at how a house would be affected by each direction of motion. When the house is shaken in the east-west direction, this shows up on the lower component. Nothing is recorded on the north-south or vertical components. When the house shifts north-south, this shows up on the second line. When the house is shaken in an up-down or vertical motion, only the top seismogram records the motion. During an actual earthquake, the house can move in all directions. Why is that? Earthquakes produce different types of waves, like body waves and surface waves, and these waves travel out from an earthquake in all directions. Body waves, like P and S waves, travel a curving path through the earth. As a result, they arrive at seismic stations from below. P waves are compressive waves that cause temporary microscopic deformation of the earth in the direction the wave is traveling. Thus, energy is primarily recorded on the vertical component of the seismogram, with less energy recorded horizontally. S waves move more slowly and are more destructive since they advance with a shearing or back and forth motion. Because S waves arrive later than P waves, they're usually seen on a seismogram as a second pulse. S waves cause deformation perpendicular to the direction of wave travel, which is primarily horizontal or back and forth motion, with less energy recorded on the vertical or up and down component. The slower surface waves, such as Love and Rayleigh waves, move in a more complex undulating pattern and thus show up on all three components. In conclusion, it is the combination of signals that gives seismologists information about the magnitude, distance, and type of earthquake that occurred.
All right. Okay, so that puts that together in a more animated way, showing how those three different components, right, X, Y, and Z, are manifested during an earthquake event. Okay. All right, so let's ask the question, well, if an earthquake happened and no one was physically there to feel and experience, how do we know where it was and how big it was? Okay. So now we can begin to use an array or constellation of seismometers around the Earth's surface to pinpoint the magnitude and location of earthquakes. Okay. So we know the velocity at which different seismic waves travel. Okay, we've empirically measured them. From our seismometers and seismograms of earthquakes, we can measure the time that elapses between the arrival of the primary and the secondary wave. So if we know a velocity and we know a time, right, we have units of meters per second and units of seconds, we can measure a distance, right? So the way that this works is that when you have an earthquake, right, here's our focus right here, boom, the primary and secondary waves are released out in every direction through the interior of the earth, right? And so they will first reach the closest station, right? So the arrival time of the primary wave at the closest station will happen first. And because there's a shorter distance to travel towards the surface from the focus, the secondary wave will have a lag time that is relatively short. As you go to seismometers further away from the earthquake focus, right, you will have a later arrival time of the P wave and a greater lag time between the P wave and S wave at each station, right? So right here we see at station 1, right, this lag time highlighted in green is shorter than the lag time at station 2 and station 3. Okay, so that is telling us the distance from that station from the earthquake focus. But here is an important thing to remember, is that you have no idea if that earthquake came from the east of you or to the west of you, if you're just looking at one spot on Earth's surface. You have a constraint on the radius in which the epicenter is. So you need multiple seismometers at different locations on Earth's surface, and you can use the lag time and arrival times between P and S waves to triangulate where the epicenter of an earthquake is, right? So if we have an earthquake monitoring station, a seismometer here at Station 1. This is like in the Canadian Rockies, right? And we record a lag time in between our P and S waves, and it's relatively short, right? And we calculate there's a 2,000 kilometer distance from the epicenter. Now we do this for multiple stations that are progressively further and further away from the epicenter, like Station 2 out here, the end of Nova Scotia, right? And we have a 4,000 kilometer distance, right? So that's a radius. And then down here in Venezuela, right? So we have the furthest distance of 6,000 kilometers, okay? So from our seismometers, we can trace a circle about that station with the radius. That is the distance to the epicenter. Where those circles all intersect with each other is the epicenter of the earthquake. Okay? So you can do this with as few as 3 seismometers. Okay? So this is telling us about where the earthquake happened. Okay? But it is not telling us about the intensity and magnitude of the earthquake. So let's first talk about earthquake intensity. Earthquake intensity and magnitude are not the same thing. Earthquake intensity is the intensity of ground shaking, and this is a qualitative measurement. So this has been around for about 100 years, and it's a intensity scale called the Mercalli scale. And there are 12 gradations of shaking that are based on observed motion that occurs near an earthquake epicenter. The intensity of an earthquake can be variable even if you are right next to the earthquake. And it depends on where you are standing, basically, right? So if you are on the side of hard bedrock up on a mountain during an earthquake, you'll feel shaking, but it will not be as intense as if you were on poorly consolidated mud, right? That mud is going to just kind of turn into jello, right, when you shake jello. So, earthquake intensity is okay, sorry about that. Microsoft being jerk today. Okay, so intensity of shaking, right? So this is, the best part of learning about earthquakes is getting to watch stuff that happens during earthquakes, okay? And maybe the worst business that you could own during a earthquake is a liquor store. Maybe a Crate & Barrel. Music is too intense. This was a big earthquake in Nepal a couple of years ago. It was a magnitude 8 earthquake. Everything's calm until the tectonic plates decided they were going to start moving and release seismic waves in a world where liquor is stored in glass on shelves and shaking occurs eventually. We're gonna fast forward. Uh-oh, here we go. Get away from that wall. They did the right thing, right? They found somewhere to protect their heads underneath something that wasn't going to get crushed by falling debris, okay? Right, so if you live in an earthquake-prone area and you have a lot of things that are, able to fall off of shelves and hit you, or it's something you don't want to break, you should be careful about that. right? But another thing that happens during earthquakes, right, is I was talking about how the intensity varies on the medium, right? You're on solid bedrock, it's not going to shake as much as something like water. So in the Philippines a couple of years ago, a rooftop pool on the top of a skyscraper started to just dump out over the city during an earthquake. Right? Because that water in the pool is sloshing back and forth really rapidly with the ground shaking from the earthquake. And then it's just dumping out over the edge. So that's kind of a unique hazard that probably should be considered more if you're going to be a real estate developer and decide that building a rooftop infinity pool on top of your skyscraper is probably not a good idea if there's a lot of seismic activity. Anyway, our earthquake intensity can vary by location, right? And so every time there is an earthquake, the USGS asks people that they go online and tell them if they felt it, because it's critical qualitative information that tells them about the severity of earthquakes, right? And so this is a global compilation map of all the different earthquake observations from people, not from scientists, but people who have gone on and told the USGS, yeah, I was in an earthquake and it felt really intense, or I was in an earthquake and there's a little rumble, that's it. Okay, so that's earthquake intensity. Now, what about magnitude? So earthquake magnitude is slightly different. It is the measure of the amount of energy released during the earthquake. This is what you've probably heard of as being the Richter scale, which is the 20th century measurement scale for magnitude. Earthquake magnitudes are measured on a logarithmic scale. That means powers of 10. So with each increase in magnitude, there is 10 times as much energy released. The way that we figured out earthquake magnitude on the Richter scale was by developing a logarithmic equation that relates the lag time, so the distance between you and the earthquake epicenter, and the amplitude of shaking recorded on your seismograph. That relationship between the amplitude and the lag time will tell us the magnitude, right? So we can relate this logarithmic scale of the lag time with the amplitude and basically connect them linearly through a magnitude scale. Okay. Now we use a slightly more sophisticated method called the moment magnitude scale. It is similar to the Richter scale in that it is a logarithmic scale, but it uses a little bit more sophisticated math and seismographs than we initially used in the 20th century. Okay. So the important thing to remember about earthquake magnitude is that each time you click up a integer value in the magnitude, right, from a 4 to a 5, 5 to a 6, you are increasing the amount of energy released logarithmically, right? So you're increasing by a order of magnitude of energy released. So in the grand scale of all earthquakes that happen on Earth, right, the most frequent are low magnitude, stuff less than 3.9. Like most earthquakes at that level, you barely will feel unless you're like really close by. But as you increase on the scale of magnitude, right, into light scale up to moderate and strong, and then severe and then extreme, there is much more energy released and the amount of devastation associated with them becomes much more intense. So a way to at least put this in sort of a more relatable scale for humans is to compare the energy released during earthquakes to more common events that we have observed on Earth, right? So if we look at the magnitude and the energy equivalent released, right? A lightning bolt strikes at one point on the ground. That's quite a bit of energy in one spot, but spread out over an area, that's really not very much. But then as you increase things like a tornado or atomic bombs or hurricanes, right, there's a lot of energy being released. And then we can see comparable earthquake events. So once we start getting into the strong earthquakes above a magnitude 6, we're starting to see very large amounts of energy released that rival very large volcanic eruptions or the most powerful atomic bomb tests like hydrogen bombs. Okay, when we get up to the most extreme great earthquakes that are extremely rare in nature but still possible, this is when we see the most incredible amount of energy released on Earth's surface. So the 3 most powerful earthquakes that have happened really in the last 100 years, the most recent being in Japan in 2011, right? These are incredibly energetic events that released a ton of energy, and that is manifested through shaking, the generation of tsunamis, and then ultimately devastation to human infrastructure. Okay. All right. Where do earthquakes occur? You already knew this. Plate boundaries. Okay. So this map is a little bit different than the other ones we've seen, right? When I showed that video of where earthquakes are occurring, it shows, the magnitude and location, right? And what's important and different about this map is that you can not only pick out the frequency, right? How concentrated those little dots are, but also the color tells you about their depth, right? So red is shallow, yellow is intermediate, and then blue is deep into the asthenosphere. Okay, so we have not thought about earthquakes really yet in terms of depth, but this is important for understanding their tectonic origin. Okay, so at divergent boundaries where we have extension or stretching of the crust, such as at mid-ocean ridges or continental rift basins, you have slip typically along normal faults, right? Where as you pull apart this landscape, kind of like pulling apart an accordion, these normal fault blocks will slip down, right, along each other. The surface effect of that is we create basin and range type mountains, like in Nevada and Utah. And the other thing that can happen is in passive margins, right? So places along the coasts of tectonically inactive coastlines, right? Like the East Coast, ancient normal faults that formed initially from the extension of Pangea and the cooling of oceanic crust, right? They are going to gradually stretch out and thin through time, and you can get shallow earthquakes along normal faults that are on passive margins. These types of earthquakes at divergent boundaries are typically less frequent than those at convergent boundaries and are limited in their magnitude. Okay, you are releasing energy by pulling it apart. You're not pushing together, so there's a little bit less energy that is generated during these. Okay, then we have transform boundaries, right, where we have the lateral plate motion of 2 plates sliding past each other. That means you typically have strike-slip faults. Transform boundaries commonly link convergent and divergent boundaries together, right? You go from convergent to divergent plate motion, and you need to have some accommodation in a lateral direction to make that transition. In these type of plate tectonic boundaries, right, earthquakes are very frequent, and they can be moderate to shallow depth, and they are capable of generating large magnitude earthquakes in the M8 realm. Okay, so the most famous one to us here in the United States is the San Andreas Fault in California. And this is the type of plate motion that happened to cause the Great San Francisco earthquake of 1906, as well as large earthquakes in Los Angeles, including the one from the makeup video at the beginning of the lecture today. Convergent boundaries, right, where we have either subduction zones or continental collisions, are where we have a range of all types of earthquakes, meaning that they can range from being shallow, very close to the surface, to being very far and deep into the asthenosphere. These can generate our largest magnitude earthquakes into the 9 magnitude region, and these are megathrust earthquakes, meaning that they happen along low angle thrust faults and reverse faults. Why don't we have earthquakes that go all the way down into the mantle? Well, remember is that as we change the pressure and temperature conditions in the mantle, we change the ductile versus brittle deformation of subducting crust. So once you reach about 660 kilometers depth in the crust, we no longer have brittle deformation, and the subducting plate can flow plastically, and therefore earthquakes do not occur. Now, what about earthquakes that happen kind of in the middle of nowhere for no reason? So intraplate earthquakes are those which occur in parts of continental crust that are not tectonically active, and they are rare, but can be quite damaging when they occur. And this is typically due to movement along faults that are from really ancient geologic structures, like ancient mountain building events or rift basins that are kind of equilibrating under changing stress. They're typically more shallow than convergent boundary earthquakes, and they can be quite problematic for humans because if you don't live in a tectonically active environment, you and your community are not used to having earthquakes, and therefore you do not build or design codes and regulations to survive those types of events. So there's a couple that are quite famous in North America. The biggest intraplate earthquake happens in Missouri, and in the early 1800s, there was a pulse of magnitude 7 earthquakes that was really quite destructive for that part of the country. But closer to home here in Vermont is up in Montreal and southern Quebec and Ontario, where there is a historical record of earthquakes occurring kind of between the boundary between Appalachian mountain building rocks of the East Coast and the Adirondacks, and then the Canadian Shield or Craton, the ancient crystalline rocks. And so actually in the 1730s, there was a really large magnitude 5.8 earthquake in Montreal that caused quite a bit of devastation in the St. Lawrence Valley as well as in the Adirondacks. And there's a grad student at UVM whose undergrad thesis was actually looking at how gravestones from the 1730 era were deformed and affected by the shaking from the earthquake that happened in the 1730s. So you have to imagine, right? Think about your apartment or dorm here at UV in Burlington, and think about, would this building actually survive an earthquake? Depends what it's built out of. Depends how you've set up your apartment. I mean, I can tell you my apartment is definitely not earthquake proof. And so if there were to be one of these rare intraplate earthquakes, what would happen to us? So it's something to consider, even though they are rare and unlikely. So then we can link all of these different fault motion environments together tectonically, right? And we can have, again, our transform motion strike slip faults, extension in continental rift valleys, which causes normal faulting, intraplate settings where we have deep geologic structures pre-existing that are adjusting to changes, and then convergent like zones of mountain building, as well as subduction zones. So for the last real lecture of class, we will finish off with earthquake hazards.